It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee. Hi guys, well, this is the first video I'm going to be doing for the using and controlling reactions, showing you some different things. So I just want to start off by talking a little bit about what enthalpy is. Okay, so enthalpy is the heat change in a reaction, and we generally give it the sign delta H. It means change in. And there's basically two types of reactions that we want to talk about. There's exothermic, okay, where energy exits, alright, so energy out. And we've got endothermic, right, where you've got energy entering, so energy in. Okay. Now what you'll notice in these ones is energy out, so you'll see an increase in temperature. In this one here, endothermic, you'll see a decrease in temperature. Okay, I go through that a fair bit in the commentary to go with the PowerPoints for this topic, so I'm not going to go into too much more detail. So what I want to start on though is talking about energy profile diagrams. So what do I mean by that? Okay, so energy profile diagrams help us to see a couple of really major points. So what we've got is a graph that looks a little bit like this. Okay, and what we've got along the side is energy. Alright, and down the bottom we've got just the products, I guess, and reactants. So there's two types we've got here. We've got reactants that go across here, and for this one, firstly, I'm going to put the products up here as well. Okay, so what we can see here, if we're looking at the energy difference between the reactants and the products, is in this case here the products have a higher energy. Okay, the enthalpy that we measure is the distance between the reactants and the products. Okay, now in this case here, obviously what we're doing is putting energy into the reaction. That's why the products have a higher energy state. You can see here that our delta H value is positive. So this is obviously going to be an endothermic reaction. Okay, so you can see from products having higher energy than the reactants putting energy in, endothermic reaction. So what we talk about sometimes with these though is, I guess, the pathway that we have to go to get from reactants to the products. Okay, and what we've got in this pathway is this energy that's required for the reaction to start. Okay, so here, if we actually put in this value here, that is what we call our activation energy, EA. So the EA is the minimum energy required. Okay, so it's the minimum energy required for the reaction to occur. So this is why a lot of reactions require you to heat them or expose them to light or do something to actually get them going. All right, we don't just have lots of chemical reactions going all by themselves all over the place. We need to actually put in some energy normally in order to get a reaction occurring. All right, and that energy we've put in, or energy that we need to get the reaction started, is called our activation energy. Okay, so that's an endothermic profile. Okay, if we look at an exothermic one, all right, hopefully you can work out what the difference is going to be. Okay, but what we're going to see is that our reactants this time have a higher energy. Okay, so here's the starting energy of our reactants. Our products are going to have a lower energy level. Okay, here's our pathway that we go along. Okay, and again there's a couple of things that we can look at. The difference between the reactants and the products here. Okay, this time is negative. Okay, this is an exothermic reaction. We're giving out energy. Could be in the form of heat, could be in the form of light, could be in the form of sound, doesn't really matter. Okay, here what we've got, the distance between the top of our peak, okay, and the reactants is our activation energy. Now remember, these are just representations, so it doesn't necessarily mean that the activation energy for this one is lower than the previous one I showed you. It's just a representation of showing what's happening in our reaction. Okay, so you need to be able to draw diagrams like this to be able to show activation energy and also enthalpy change. Okay, now what I want to go on to is talking about how we calculate delta H from a reaction. Okay, so we've probably by this stage you've already had a look at doing some in practicals. Okay, and so what we want to look at is a couple of things we want to look at. Okay, is this number up the top here, 4.18. Okay, this is what we call the specific heat capacity of water. Okay, and this value is telling us that it takes 4.18 joules of energy, all right, to increase 1 mil of water by 1 degrees Celsius. Okay, so obviously when we're doing these calculations we run some assumptions. We assume that the solutions we're using have the same density of water, all right, and we also assume they have the same specific heat capacity as water when we're doing our calculations. Okay, so to calculate our enthalpy we use delta H equals 4.18 times by the change in temperature times by the volume over 1000 times the number of moles. Okay, so our change in temperature here, our delta T, is our final, is our initial, take our final, it's my brain jumping ahead of myself, sorry, initial, take a final. Okay, so hopefully you can see if we have an endothermic reaction, our initial value is going to be higher. So if we had a reaction that started at 23 degrees Celsius, alright, so that's the start, and the end point was, say, 14 degrees Celsius, okay, 23 take 14, okay, 23 take 14 is going to give us 9, alright, that's a positive value, so you're going to have all positive values as you go through here, which is going to give us a positive delta H. Obviously, on the other side, if you have a end point which is, say, 44 degrees Celsius, right, you've got 23 minus 44, you're going to get minus 21. Okay, so putting a negative value into here will give you a negative delta H value, which is exothermic as well. Okay, the other really important thing to remember is that our volume is in milliliters in this one. Okay, always, because we come back to this specific heat capacity of water, 4.18 joules to raise 1 mil of water by 1 degree Celsius. Okay, the other thing in there is number of moles. Generally we do that by molar mass divided, mass divided by the molar mass, just like you've done in the titration and stoichiometry topic. So if you can just plug those values in, you'll get your delta H value. Now the units we always get for this are kilojoules per mole. Okay, so this bit up here, I'll just switch to a different colour. Alright, I'll go for green. This bit up here, 4.18 times delta T times V, tells us about the energy involved in the reaction. So it's either the energy released or absorbed. Okay, so we can use that to work out the energy. And that is in joules. Okay, so if you divide joules by 1,000, you get kilojoules. If you then divide it by the number of moles, you get kilojoules per mole. So anytime we write a thermochemical equation, we use kilojoules per mole. So you can just pop that in there. There's an example of that in the notes. Hopefully you've gone through plenty of them as well, so have a look at that if you need to actually see an example as well. So, you know what an exothermic reaction is, you know what an endothermic reaction is, you know how to calculate your enthalpy value from a practical, measuring the temperature change, looking at the volume of water that you're heating up. So now what you want to come to are what we call thermochemical equations. Okay, and there's 4 parts to thermochemical equations. Number 1, you need to have the correct, what we call species. Okay, so that means you need to be able to know that carbon dioxide is CO2. You need to know that butane is C4H10, which we'll get to in organic if you don't know that already. Okay, so you need to have those. That's the same as any other sort of equation. Number 2, it needs to be balanced. Okay, so that's kind of the basis of all your chemical equations, but thermochemical equations require 2 more things. Number 3, they require the state. So by the state, we're talking about solid, liquid, gas, or aqueous. Okay, and fourthly, they need your delta H. So you need to show whether it's positive or negative, and you need to generally have a value in there. So I'll show you how we write one of those. Okay, so let's take something like methane, okay, CH4, okay, and we burn it in air. So just a simple combustion reaction. Anytime we're looking at combustion reactions, we're assuming complete combustion here, so we're getting carbon dioxide plus water. Okay, we balance it up, we need a 2 in front of that, we've got and a 2 there. Okay, so we've got our balanced chemical equation. So first we've done the correct species, everything is correct, we've balanced it. Okay, next step though is we need to put the states in. So methane is a gas, oxygen is a gas, carbon dioxide is a gas, and water in combustion reactions, you've got to think is there's lots of energy released in combustion reactions, so it's going to vaporize the water. So we've got a gas there. Okay, and then what we need to put in is our delta H. So you put the little semicolon there, delta H equals, you put your value in this case it's going to be negative something rather, negative kilojoules. Alright, and that's the thermochemical equation. You can see other sorts. If you're looking at enthalpy of neutralization is always 1 mole of hydrogen ions with 1 mole of hydroxide ions, okay, giving us 1 mole of water. Delta H is always, in this case, negative 57 kilojoules per mole. Okay, so that's your thermochemical equation. If you can just always remember to write your correct species, then you balance it, then you put your states in and put your delta H in, you'll get your 4 marks in the exam. So that's a lot of marks. That's 2% of your grade just for one equation. So you really want to make sure you can get them right. Alright, so that's a real kind of quick introduction to thermochemical equations, to enthalpy, to exo and endothermic reactions. Just remember, go back and practice those diagrams of being able to show the activation energy, the enthalpy, practice doing some calculations on determining your enthalpy, and practice writing your thermochemical equations. Alright, if you can get that basis for the start of this topic, you'll be doing fine. Okay, see you guys.